Okay, and let's get started. All right, so we're gonna go back and take a quick review of what we have done from last lecture, okay? On Wednesday, we talk about how we do one-way slab. All right, so this is the notes we collected. Yes, can you speak louder? Any question? Okay, all right. So here, we talk about the one-way slab, all right? So first of all, to make sure we have a one-way slab, we need to make sure that the span length in the other direction, which is L2, so I'm gonna use a red, L2 here, and divided by L1 is bigger than 2, okay? So the shortest span length, L1, is actually the span length for this one-way action. So that's why it's called one-way action. And I forgot to mention that some of you might be asking, okay, Bob, this is one-way action. Do we have situation we have two-way action? Yes, we do. Yes, we do, okay? So for the two-way action, usually we're talking about L2 and L1 is roughly between, say, 1 and actually 1.5 range. These are typical two-way actions, okay? These are two-way actions. And these are a little bit complicated. It's a little bit complicated. Not actually particularly about the flexure part, it's about the shear part. Okay, so I'm gonna talk quickly about it. So for one-way action, okay, so this is the beam, and this is another beam. So you only have shear here, and shear here, and the bending, which is maximum, supposedly at the end, and the negative moment at the middle, sorry, at the support. Okay, positive moment in the middle and negative moment at the support, okay? This is for one-way slab, all right? For two-way slab, things a little bit complicated. Okay? So usually you have this kind of squarish thing where you have the beams underneath it, supported all around. So in this case, you have to worry about the shear and moment. But in this case, normally we'll actually have a distribution line to tell you how much of a force distribute to each of the part of the slab. Okay, so then we have to calculate the moment, and the moment may not be the maximum right in the middle. It might be in this line here, and the shear might be here, 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 here. So it's quite complex. Okay, so quite complex. All right. So in this course, we only talk about a one-way slab here. Okay, one-way slab here. It's just a little bit easier. Okay, but if you have time, you can go over the two-way slab in the textbook. Okay, so this is available. Okay, Michael, do you have any question? Can you speak louder? I can't hear you clearly. Okay, you dropped out. All right. So again, if you have trouble making yourself heard, you can text in the chat. So I'm monitoring them live. So if I see any message, I'll stop and try to answer your questions. Okay. So please feel free to answer questions, ask questions whenever you feel like to. Okay. All right. All right. So I'm just going to go ahead. These are basically different between one-way and two-way slab. Like I said, the two-way slab is a little bit complicated. So normally we'll just talk about one-way slab in our course, okay? Then again, if you're interested, please go back to your textbook to take a look at the two-way slab and let me know if you're interested discussing details. I'd love to go over with you, okay? All right, so this is the concept of one-way slab. We talk about how we're gonna analyze it. We say we're gonna use 1 foot, 12-inch of strip to do the one-way slab analysis, We went down, talk about how we're gonna do it, and it comes down to a area per foot. Area per foot. This area is actually a reinforcement area. Okay, and there's a conversion we have to do, which actually had to convert the area of bar presented in this strip back to the required area over foot. Okay, back to the required area per foot. Okay, and then we talk about deflection control spacing, which actually require that the bar have to have a spacing less than the maximum spacing, which 3 times the slab height, or 18 inches. Okay, and we also have another limitation is the maximum spacing. Okay, and this maximum spacing is by the correct controlled spacing. Okay, it means the spacing has to be less than this or less than that. And note that there's a symbol here, Fs is 2/3 Fy. Okay, so hence we come out with this equation here. Okay, AB multiplied by 12 divided by required area per foot. Okay, this is through calculation. And 3 HF and 18 inches deflection controlled requirement, deflection control requirement. And this is crack control requirement, okay? And sorry about that, but I forgot to mention there's also a minimum reinforcement area requirement. So AB is our AS mean, okay? AS mean is actually 0.002 BHF in this case, okay? And this you can find out from ACI 10.5.4. All right, so I missed this part from last time. Please add it to your notes. Okay, this is the minimum requirement for the area of steel. Okay, area of steel. All right, okay, so now this plus everything else, right? This plus everything else. It's the requirement for longitudinal differential. How do we determine AV min? Do we need to know VU? No, we don't need to know the shear to determine this. Everything we're talking about right now is about flexure, okay, bending. Okay, so remember when we talk about here, we have is AS per foot, AS per foot, AS per foot. Okay, this AS per foot is the AS mean target right here. So all we need to do is just to compare, add one more process step. Okay, AS per foot to make sure this has to be bigger than AS mean. Okay, so that's an additional thing we have to, follow, okay, besides the spacing requirement. Is that clear? Is that clear, Anna? You need more information on this, or we're good? Okay, all right, well, we're gonna have an example right after this, okay, so you see better, okay? So this, on top of all this, I label as one, this is flexure reinforcement, okay? Flexure reinforcement means it's only care about bending, okay? And all these reinforcements, okay, are talking about bending, okay? There's no shear involved, okay? We don't really care about shear in this case, okay? So be sure to memorize how the requirement condition relate to control type. You don't have to remember, okay, these specific equations. Is it for deflection control? Is it for crack control? You don't have to know that, okay? But in the exam, you have to be able to know how to calculate it, okay? So this is AS, again, let me emphasize, this is AS mean, okay? This is for bending, all right? This is for bending, this is not for shear, okay? So in one-way slab, we only talk about bending right now, not the shear, okay? Shear is supposed to be covered from the previous lectures, okay? All right? So that's category one, means flexure. Category two, we actually have to consider shrinkage and temperature. But be careful here, okay? This shrinkage and temperature reinforcement is in a different direction. It's a label here, okay? It's a different direction. All right, since we already have flexure reinforcement, and this flexure reinforcement already take care of the crack and deflection, usually they're more than sufficient to take care the shrinkage and the shrinkage and the temperature in this main span direction already. So these additional reinforcement, okay, this additional reinforcement is on the other span length, right, along the other span length, the other direction. Okay, so here, this AS means different from previously, okay? Although the form looks like same, but it's different, okay? So think of it, it actually makes sense because this is also the shrinkage and temperature requirement for the span length in L1, okay? This is also for L1. But just to make sure that we will definitely have sufficient reinforcement bigger than that. Normally we do, okay? But in this case, we only care about the shrinkage and temperature in the other direction, which is L2. And these are the equations for L2, for the minimum reinforcement area for L2, okay? And again, this will be compared to AS mean has to be smaller or equal to AS Okay, AS provided. AS provided. Okay, and again, this is per foot. All right, this is per foot. This is per foot. All right. Okay, so now, and don't forget, okay, this is effective area. Okay, this is effective area. Okay. All right. Good. Okay. Now, oh, sorry. This is actually. Let me make sure. This is a little bit error here. Somehow I read it wrong. This is BH. Okay. BHF. Okay. And we'll show you an example later. So don't panic. Okay. Show you an example. Okay. Show you an example. All right. So to give you a little bit detail, okay, so we show this plan view again and show the detail of the bars. So there are two directions. These dots, right? These dots in the L2 direction, these are shrinkage and temperature, S and T, okay? Shrinkage and temperature. Now these longitudinal bars are flexural reinforcement, okay? Longitudinal bars are flexural reinforcement, okay? So these are two different directions. Now, last lecture, we also shown you an example. We shown you an example, right? We have a simple span, 10 feet, apply moment, 315 pounds per square foot, calculated. And we talk about the minimum slab height, HF, by this ACI 9.3.1. You can use that table to get this. And then assume we have a height, which is 5 inches. And we now estimate the depth of that, which is 4 inches. That's depth of that, which is 4 inches. What was the correction AG? Okay, sorry. So it was previously L1 HF because we talk about the hole. And now we'll just replace that with B. Okay, replace that with B. And this is actually a strip, 12-inch strip. Okay, and then we're also showing an example, so don't worry, okay? We're showing an example, don't worry, okay? Sorry about this typo previously, okay? And now, let's take a look. So we estimate the depth by this way, okay? And keep in mind, we assume for number 4 for the reinforcement for slab, okay? And typically it's either number 3 or number 4, okay? These are commonly used, okay? I just want to label here, commonly used. Okay, so these are the assumptions: 5-inch height, 4-inch depth, number 4 bar assumed, and we went along with that, right? And we estimate the dead load by using this geometry and get the dead load. And last time, Jordan, we talked about this unit, right? So if you still have a question on this, this is pound per square foot, okay? And why we have a pound square foot? Because I have height, and remember this is per foot, okay? And then we have this 150 pounds per cubic foot. And now we have a pound square foot here, okay? And this unit will carry through, okay? Will carry through our calculations, right? And then we have the factor load. We calculate the moment by simply supported uniformly distributed load, and this is a moment per foot, per unit strip, okay? Per foot unit strip. All right, then this is a typical flexure design, right? We assume tension control to start with, right? And then we calculate the pre-estimated required steel, right? So this MU per phi FYD half A, and differences here, we use an approximate JD roughly equal to 95% of depth, which is slightly higher than beam, okay? And then we went down with this equation and get this number here, okay? And we'll make sure that the unit works. We actually get inch square per foot, okay? And then we confirm the A by the pre-calculated AS, okay? And we get this is 0.339 inch per foot. We always have this per foot in the one-way slab analysis, all right? So at this point, I have the actual A, so I'm gonna bring it back to here to recompute my required area AS, okay? Because I have actual A. So this is where we're gonna start today's lecture, okay? So let me go back to blue. All right, so now, since I have A, since A is already known 0.339 inches, 339 inches, okay? And with that, I'm gonna say the required steel AS has to be bigger or greater than MU, applied moment on top, phi, strength reduction factor, Fy, and D minus half A, So I bring the number in, this is 3.94 kips a foot per foot, and multiply 12 inches per foot, 12 inches per foot, and divided by 0.9 strength reduction factor, 40 KSI yield strength, right? Grade 40 of steel yield strength, and the depth of the slab 4 inches minus A. What is A? A is 0.339 divided by 2. Okay, so this I got a number for AS equal to a bigger or equal to the 0.343. 0.343 inch square per foot, inch square per foot. Okay, so now once I have that, I need to select bars. I need to select bars. All right, I need to select bars. Okay, so to start, I'm gonna assume or use number four stirrups. Use number 4 stirrups. Okay, for this is number 4, then I want to compute, right? So the AS per square foot, by the way, this is per square foot, has to be smaller than equal than AB bar, area of the bar, okay, and multiplied by 12 inch per spacing in terms of inches, Okay, now make sure this is AB, which is number 4, so area is 4 for AB, so it's 0.2 inch squared, number 4 bar. 1 number 4 bar. Okay, this is 1 number 4 bar. You agree with that? So this gives me that the spacing has to be smaller than AB multiplied by 12 divided by AS. Okay, divided by AS. So this is 0.2 multiplied by 12 divided by AS. What is AS? This is 0.343. Okay, 0.343. I get this spacing to be 7.06 inches. Okay, this is spacing. This is spacing. Ah, so sorry. I really don't like Apple Pencil. Somehow just not so neat. All right. So 7.06. Okay, that's the spacing. All right. So this is the spacing I'm going to use, and this is the bar size I'm going to use, and this is not stirrups. I keep messing it up. Okay, it's number 4 bar. Okay, this is not stirrups. Okay, this is bar. Okay, flexure. Just make sure. Still in category 1. Okay, so with this two information, I'm going to say we're going to use number 4 bar. Okay, at a spacing of 6 inches. Okay, because 6 inches is smaller than 706 inches. Right now, just to make sure, I want to compute what is actually my AS per foot in this case. So AS per foot provided would be equal to 0.2, okay, multiplied by 12 divided by 6 inches. So this gives me a number of 0.4 inch square per foot. This is provided steel. All right, this is provided steel. Highlight that. Just red. This is provided. Okay, this is provided. All right. So at this point, I think we're fine. But again, don't forget, by our flash design, we need to confirm yield and also tension controlled. Those are the assumptions we made at the beginning, right? So A, the compressive zone size, equal to AS Fy divided by a 0.85 F prime C B. All right, and this equal to 0.4. Okay, this is 0.4. Where that coming from? That's the provided steel. All right, inch per square foot multiplied by 40 KSI of yield strength divided by a 0.85, the Whitney stress block factor, and 4 KSI of a concrete, and 12 inch. Okay, 12 inch of the width. And this B is the strip width. Right, per foot. It's 12 inches. All right, so with this, I got my A equal to a 0.392 inches. That is my actual compressive zone. That is, well, effective compressive zone, right? So this is effective compressive zone. Okay, and to get my actual compressive zone C, small c, I need to use A divided by beta 1. A divided by beta 1, all right? And I got 0.46 inches. 0.46 inches. And remind us again, what is beta 1 here? Beta 1 is 0.85 for F prime C equal to 4 KSI. Remember? Okay, those are the Whitney stress block equation, right? Factors. And now with that, I can calculate the strain and the tension, the last layer of steel, epsilon T. In this case, I assume it's one layer, right? One layer, all right? Because it's actually number 4 bar at 6 inches. So it's one number 4 bars per 6 inches, one layer reinforcement. And that equals D minus C divided by C multiplied by epsilon Cu. And this is 4 minus 0.46 divided by 4, and epsilon Cu becomes 0.003, and I have a strain of 0.03, 10 times than that, right? And it is bigger than 0.0207, which is yield strain, so yield, all right? And this number also happens to be bigger than 0.005, 0.005. Do I miss a 0 here? Yes, I missed a 0 here, okay? 0.005, which means it's tension controlled. Tension controlled. All right, so I finished my check here. It's tension control. I'm gonna go back and calculate my nominal moment resistance. So Mn now equal to As Fy D minus half A, D minus half A, and calculate that, save the time, which is 5.1 kip foot per foot. Okay, kip foot per foot. And if I do a phi Mn, which equals 0.9 multiplied by 5.1, I got roughly a 4.56 kip foot per foot. Okay, which is the bigger than the ply, which is what is applied here. Let me check real quick. What is applied here? 3.94, right? 3.94, so 3.94 kip foot per foot. Hence, we're okay. Okay, this is over. Switch C in the denominator with D. Did I do that? Switch C in the denominator of D. Oh, so sorry, you're right, absolutely. Let me correct it, okay? So sorry, this is an error here. All right, equation's right. The number, I got it wrong, okay? Sorry about that. Fix it here, okay? 0.46. Thank you for reminding me that, all right? And now that is VMN. So I got a 3.94, sorry, I got a 4.56, which is bigger than 3.94 kip feet per foot. All right, but this is not over yet. I just need to check, make sure my AS min is satisfied. AS min is covered, Remember, has to be bigger than the shrinkage reinforcement. So AS min equal to a 0.002 BH. Okay, so this is actually AG, as shown before, and this is 0.002 B. As we all know, it's 12-inch is strip width, unit strip width, all right? And I got a 5-inch of slab height, so case B, HF, all right? HF. And this number I got is 0.12 inch squared per foot, okay? Don't forget. So you may get a little bit confused. So I have this here, inches. I have here inches. Where that preferred coming from? That preferred is buried in this factor here. All right. So with that, I want to compare what's provided. So AS provided, POV provided equal to what? What is our provided? Provided is 0.4, right? 0.4. Provided is 0.4. So it's 0.4 inch squared per foot, which is much bigger than the minimum requirement, which is 0.12 inch squared per foot. So we're okay. Finally, all right? Finally, we're okay. All right? But again, like we said again, don't forget, check the as max spacing, eh? The max spacing, right? So for me, I'm gonna say for deflection control, you don't have to write this again in the exam, but you need to remember the equation, all right? So for deflection control, it's got to be 3HF or 18 inches. So in this case, what is the governing? It's 15 inches because this is 15, right? HF is 5, so this is 15 inches. So the provided, right? The provided spacing equals 6 inch, which is smaller than S max, which is 15 inches. So, okay. Okay, and also now crack control, S max equal to a smaller of 2, right? Smaller of 2 equations. 15 multiplied by 40,000 divided by Fs and minus 2.5 cc. All right, so let's bring a number in. This is 15. This is 40,000. Bottom here, 2/3 of grading, strength of the grading. What's the strength of the Fy is? Fy is what? 40. Oops. Fy is 40,000. So happen to cancel. The minus a 2.5. What is cc? 0.75 inches. If you forget, go back all the way back to when we make assumption on this. So cc is 0.75. Okay, cc is 0.75. Okay, so now with all this, I got a number equal to a 20.6 inches. Okay, and now don't forget there's another equation, 12 multiplied by 40,000. Again, Fs. Okay, and this I have a number of 18 inches. 18 inches. Okay, so comparing this 20.6 and 18, of course, 18 smaller, so governs. And provided, as provided, equal to 6 inch, which is smaller than S max crack control, in this case, 18 inches. So we're okay. We're okay. All right. So at this point, we can say fracture reinforcement has been determined. You don't have to write this in the exam. I write it just for the notes, clarification of the notes. And that is number 4 bars at 6 inches. And it gives me an AS per foot of 0.4 inch squared per foot. Okay, so this is the flexure reinforcement calculation. But this is not over. Okay, this is not over. So second step, determine reinforcement, shrinkage, and temperature reinforcement. Okay, so for that, we can go directly into the equation. So the equation says AS min, remember from the previous lectures, AS min. So there's a series of equations. So let's just go back real quick, review what we have written here. So AS min has to be largest of 0.02 Ag, 0.08 Ag, or 0.018 Ag. Scroll up here. Okay, Ben, just a second. Okay, so let me just try to illustrate this part. I'll scroll up real quick. Okay, so these 3 equations we need to pick. Now, in our case, Fy is 40 ksi, so we only need to pick this equation. Okay, so now let me show you what we have. So first of all, we have checked the flexure reinforcement, and we need to determine the shrinkage and temperature reinforcement. So AS min, given that Fy equal to 40 ksi, I'm gonna use only the first equation, which is 0.002. B H, so 0.002. B is 12 inches. HF is 5 inches. So I got this number to be a 0.012 inch squared per foot. Inch squared per foot. Okay, so for this case, okay, I need to choose bars. Okay, did I mention there's also a spacing requirement? I think I should have mentioned there's also a spacing requirement. Okay, this is strange. All right, anyway, let me go back here, okay? So for this, this is calculated. So I'm gonna set a limitation on S max spacing from previous case, all right? And for the max spacing, I need equal to 18 inches from previous case, one, okay? Okay, for the spacing, and this is from deflection control spacing, all right? So we say if I'm gonna use number 4 bars to satisfy these two requirements, so I can just set number 4 bars within 18 inches spacing, okay? And with that case, I have AS provided to equal to a 0.2 multiplied by 12 divided by 18. So this number comes out to be 0.1333 inch squared. I got more 3 here. Should I have 133 inch squared per foot? And this number is bigger than 0.012 inch squared per foot. This is AS min. So we're okay. So for the shrinkage, right? So for shrinkage, S and temperature T, we use number 4 bar at 18 inches. Okay, so just to give us a visual understanding, right? Visual understanding. So this is saying if I have a one-way slab, all right, and I have one-way slab direction of L1, this is the main direction, and L2, this is a side direction, and the main direction, the main reinforcement, let me use different colors to see better. So the main reinforcement is gonna go this way. And this is gonna be number 4 at 6 inches. The other shrinkage and temperature is gonna go this way. And this is gonna be number 4 at 18 inches. Okay, so now this is the design for the one-way slab. All right, design for a one-way slab. Okay, so before I move forward, any other question with this? Any other question with this? All right, so some of you may ask, okay, so Bob, this is one-way slab, this is nice, but how are you gonna make an exam with this, right? How are you gonna make up an exam with this? So this is a possible problem you're gonna look at, okay? So for example, for instance, I have then plan view. So it reads like this, just like shown before. So I'll have a beam, have this, and I say this is a column, and have another beam like this. This is a column, okay? And I have another beam like this. This is the column. So I'll say, okay, I have another beam like this cross, column here, column here, column here. And I'll tell you, right? Say this is A, grade A, this is grade B, and this is bay 1, this is bay 2, this is bay 3. And I will give you some dimensions. I'll probably tell you this is some length, say L equal to, say, I don't know, 10 feet here. And this is 10 feet here. And I'll tell you, okay, from support, center support to support. All right, so this is 21 feet, 21 feet. Okay, so L is 21 feet. So now I'll ask you, okay, and I put the number this way just to play with you, right? Just to play with you. And then I'll ask you, okay, which one is which direction is the one-way slab direction, right? One-way slab span. Okay, so you can tell, right? And then I'll ask you, say, if the live load equal to 150 pounds per square foot, and the slab is normal weight concrete, F prime C equal 4 KSI, and you're allowed to use grade 50 KSI for steel and design reinforcement for it. Right? So this will be a typical problem I'll give you. Okay? So now we finished the one-way slab. We finished one-way slab. Okay? So let's take a quick look what we have talked about before, right? So we have talked about overall concept, what is one-way slab, a specific geometry in the plan view, what is the reinforcement definition, per strip analysis, maximum space requirement, and we got into example and close it with this analysis. Okay, all right. Okay, so this is actually one-way slab, one-way slab. All right, now I'm gonna back out a little bit and open a new notes. All right, so let me change this to be lecture Thursday. Okay, and this is one-way slab continuum. So one-way continuous slab. Ooh, sorry, continuous. Well, this is probably fine. Okay, one-way continuous. Okay, so what is one-way continuous slab? Okay, now we're not going to be finished the continuous slab today, but I'm going to open it up so you can see it. You can see it. Okay, so when we talk about one-way slab, we actually just have a simply supported beam. All right. So recall one-way slab in last lecture has support conditions as this. Simply supported. Okay. Now this is typically for post cast slabs or slabs assembled on site. Okay. So for monolithic or continuously construction, we often have continuous slab. Okay, so for that, right? So we can show some examples. For instance, I have a column and slab joint, column slab. So this is column slab, right? Or column beams actually, it doesn't really differentiate. So for example, this is column slab system, okay? Or I have a slab integrated in girder and then, so sorry, let me try this, draw it right. And then integrated in column. So there's gonna be a cap here, okay? So I have a girder here, and I have a column here. Just clean this up to draw a better picture. Ah, so sorry. Okay, this is not my expertise in drawings. All right, so I'm gonna try to draw this nice here. Cap, cap. These are horrible, but this is the best I can do. All right, so sorry about this. Now, all these, right? So this is stepped column slab system. Okay, for all this, eventually you're looking at a system like this. Okay, a system like this. All right, so let me give some names. This is A, for example, this is C, and I call it B in the middle span, and this is D, E, F. So normally, if I want to find out the moment at B, I'm going to draw the influence line. So the influence line for moment B and B is going to be looking like this. All right. So you should be very familiar with the influence line concept from structure analysis. Okay. So if I were to draw an influence line for moment B, since the moment B is a bending, so I'm going to rotate, remember? I break it at B and rotate. So this will flip up as a straight line here and broken down like here, and then bend it like this, and come back up and bend it, come back up all the way up to here. So this is the influence line. Okay, influence line, IL. Okay, so now to have the maximum loading, to find the maximum moment, I need to use this influence line. Okay, so apparently, if I want to find out, say, the maximum possible moment, I need to load it here. I need to load here. And if I have more, actually, let me extend it a little bit. Okay, let's see, FG. And this is red. And I have loaded here to have the maximum, because this is positive, this is positive, positive, this is negative, negative. Right? So to find the maximum moment, actually, I need to do is plus a distributed loading C, D, E, F. C, D, E, F, G. So sorry. A bit messy today. Clean it up. Okay, good. So now, if I want to have the maximum possible moment, so I'm going to have a loading here. The different color is better. Use a blue here. So I'm going to have loading, distribute loading here, and distribute loading here, and distribute loading here to achieve the maximum moment. Okay, so if I want to find to find the maximum negative moment, instead of this, I need to use a different setting. Hey, I need to use different settings. I'm going to use different color. So I'm going to use this. So this is loading here. So this is positive. So this is negative. And this is positive, positive, positive. So purple here. I have negative. It's not purple, it's pink. Negative, negative. Okay. So what's going on here? What's going on is saying that I have to apply different pattern of loading to achieve maximum moment, positive and negative moment. So this gets a little bit complicated. And also, this is only for B. Okay, this is only for B. What if I want to do a moment for A, C, D, E, F, G. So this is A, C, D, E, F, G. So what if I want to do a negative moment C, right? So for instance, if my influence line for negative moment C gonna go like this. Okay, so if I want to have the maximum negative moment, I'm going to draw my loading directly, okay? Negative moment. So I'm going to have loading here. And I'm going to have loading here, because these are negative. And I have a loading here. Is that right? Is that right? So this is getting a little bit complicated. Why? Because you realize I have to keep shifting my loading to get a different maximum moment at different locations. Okay, so we actually need a moment coefficient from ACI to determine the design moment at each location. Okay, at each location. Okay, all right. So I'm gonna stop here. And next lecture, which is Monday, we'll talk about how we're going to find out this moment coefficient for continuous slab or beams. Okay, for continuous slab or beams. All right. So again, we canceled the office hour on Tuesday because I was sick. Sorry about that. So I'm having a little bit extra time right now. If you have any question regarding your homework or any other things, you can ask right now. Okay. So let me stop right here. And I'm ready for your questions. Okay. Any questions for me? You can speak up or type. Okay. Homework earlier. How do we determine a mean? Do we need to know VU? Oh, okay. Sorry. So you were referring to the homework. How we determine a minimum shear reinforcement? Do we need to know VU to determine minimum shear reinforcement? We don't need to know VU to determine the minimum shear reinforcement. Actually, there's a requirement. You need to determine the, let me go back to the notes, see if I can find you that. Okay, so let me share my screen. AirPlay, okay, just a second. Okay, so if you see from our lecture notes, open up the chat so I see it. Okay, so now if you see from the lecture notes, for VU smaller than half of VVC, you don't need any stirrups at all. Means there's no minimum reinforcement needed. Okay, so the minimum reinforcement needed, which I crossed out here, actually come from the spacing. So in our design, we were given the bar. So you don't really have to worry about the minimum shear reinforcement. You can just use the bar to determine AB and actually just determine the spacing. Okay, so in a sense, if you're talking about the minimum reinforcement area using this, then you need to know VU. Well, in this case, since this is between VVC and half VVC, so you don't need VU. But in this case, When VU is bigger than VC, you need VU, right? Because this equation has VU in it. All right, but technically, you don't determine the minimum shear reinforcement area. You determine the spacing. Okay, is that better? Is this okay? And now, any more questions on this? Am I clear? Is this okay to you?
Dr. Bob,
Yeah.
I was curious. So I couldn't find in our notes for lambda when you did the example problem. How do
So
you determine what lambda is? Because I saw you just had it as 1 in the example problem, but I was curious how you got the value of lambda.
right. So we actually have lambda in the previous equations, and we talk about flexure. So lambda always equal to 1 for normal weight and equal to 0.75 for lightweight.
Okay,
Got it?
got it. Thank you.
Good, sure. Okay, all right. So thanks, Anna. So I think that's clear. Now, Ben, overview. Yes, for overview, I want to use extra time. What I'm going to do is on Monday, after we're done with our lectures, I can either go a little bit longer than that, or if you prefer, we can have it in the office hour on Tuesday. Regardless, this overview will be recorded, so you can view anytime, and the notes will be shared as well. Okay? All right, good, cool. So any other questions regarding the homework or anything else you have concern, some problem up so far with this online formatting? You know the format, yes. So I have heard from some professors and also professor from Springfield campus. They're using a proctoring software. I'm trying to try it out tonight myself. So if I like it, I'll ask this professor how we're gonna do it. So the latest I'm gonna know is a weekend on Saturday, because tomorrow's a Friday. I think he's gonna get back to me on Friday. So I'll make a decision on Saturday, okay? And once I know that, I'll send the email out to you guys and know the format. But even if it is like online exam, it's more like a take home. Basically, you just do it online with your computer and you have time and you can practice it. So I make sure of that. And again, also for the exam, it's going to be longer than the in-class exam. I try to make the problem a little bit longer, but not in terms of solution. Okay, more of a content that cover a little bit wider area than used to cover. Okay, all right. When we had known the format, okay, in my MT course using Proctor for testimony, they did test run today so far, 75% internet not strong enough for the support program. I see. That's a very valuable input. Okay, is 75% internet strong enough? Proctor doesn't work well because of RAM issues. I see. Okay. If that's the case, I will have to weigh. Well, I have to maybe to choose the take home. The only reason why I don't like the take home too much is that the problem is going to be a little bit long, and I will give you more time, but you find it probably a bit harder to do. And I don't think the group discussion can help you even if you try. But let me try to do this, okay? Let me try to decide this Saturday. I'll take your suggestion all into consideration before I make a decision on Saturday, okay? All right, any other questions? Any other questions to me in terms of course? Online formatting is a little bit frustrating to me because I cannot see your responses. I have limited interaction with you guys. So I hope I can utilize this office hour to communicate with you guys, see if there's anywhere I can improve to make it better. So you can say whatever you want, okay? And let me stop recording for that, okay? So you don't have to worry about that. Let me just stop recording for that.